All right, well, I'm going to start the recording and also the lecture. What we're going to talk about today is a new topic. It's about floating point number representation. Because so far we have talked about unsigned representation, which is a direct translation of base representation. How we convert a value to a specific base. We talked about how to convert to base 2. And then we talked about signed representation because we need to represent negative values using only zeros and ones. So we talked about 2's complement, which is basically 1's complement plus 1. That is used to do the arithmetic negation. And what we'll do today is to talk about the floating point representation, which is how we represent numbers like pi or the natural log constant. Basically, it can represent a huge range of values. It can represent very small values. When I say it's very small, I'm talking about the absolute value. So we can represent, 1 times 10 to the power of negative something. Okay, some really, really negative powers of 10. And it can also go up to, 10 to the power of some really kind of positive exponents of 10. But it doesn't come without sacrifice. Okay, so we have to sacrifice something to be able to handle that range of values. So that's why we are going to talk about floating point number representation. I think we can talk about and finish all the theoretical topic today. It is the conversion from base 10 to base 2 that is going to take some time to get used to. All right. So are there any questions about what I have talked about so far about floating point number representation? No questions? All right. So if there are no questions, let me run the script on my local side so I can use the stylus, because I think using Zerno may be important today because I need to write a lot of stuff that is potentially difficult to represent using just text. All right, so when you go to this slide here, the first thing you notice is it has a hyperlink, and the hyperlink goes to a Wikipedia page, and that's where we're going to go first, because I do want to show you, just pictorially speaking, what we are talking about. A double precision floating point number is 64-bit wide. So that's why we went from bit 0, which is all the way to the right-hand side. Bit 0 is also known as the least significant bit, or LS lowercase b. And then as we go to the left-hand side, we go all the way to bit 63, which is the most significant bit. But this is the first time we look at these 64 bits, not as one thing, but as 3 separate things. Okay, so we have a signed bit. This assigned bit here, which is bit 63, its only purpose in life to indicate whether the value represented by the rest of the 63 bits is positive or negative. If the signed bit is 1, then it is negative, otherwise it is non-negative. That's the one job of the signed bit. The next portion we have bit 52 to bit 62. Those, which is in green in this picture, those 11 bits are interpreted as a unsigned value, as an unsigned integer. So we basically look at bit 52 of the entire thing as bit 0 of the unsigned integer. And if we look at bit 62, we look at bit 62 as bit 10 of the unsigned integer. We'll talk about what to do with that integer later on. But basically the green portion is essentially an unsigned integer. What you see here as pink or salmon is the rest of the floating point representation. It is the fraction of the mantissa in the quote-unquote scientific notation. So we'll go ahead and talk about the scientific notation. We'll talk about the mantissa, and then we'll kind of circle back to look at this picture and say, okay, but how do we do this in base 2? Okay, so we'll deal with base 10 first, and then we'll come back and look at base 2. Do we have any questions at this point about what we are going to talk about today? Nope. Okay. Is everybody familiar with the base 10? Yeah, go ahead.
Not sure but the lab for the floating point is at 1150.
Sorry?
The lab for is at 1150.
1150. Oh, that might be a mistake.
Okay.
Yep. I don't think you guys are supposed to start on it just yet.
Yeah.
Yeah, so don't worry about it. I'll fix that at the end of the lecture. All right, so let's go take a look at Zernal, and I'll go present a few cases of a base 10 scientific notation. All right, so a scientific notation in base 10 looks like this. Okay, so if I want to represent, let's say, the population of the world, okay, I have absolutely no idea what it is right now. I think it's close to 8 billion, not quite at 8 billion yet. Is that correct? Okay, so we'll just say it's 7 billion, 7,981 million, and so on. Okay, so I'm just going to use this as a number, but the quantity can now be represented by this times 10 to the power of 9, because that is what a billion is. So do we have any questions about this? Is 7.981 billion, because 1 billion is 10 to the power of 9. Are we good here? Okay, so this is what we call the scientific notation. In the scientific notation, we separate a value, or how we represent a value is separated into two parts. The first part here is what we call the mantissa. So mantissa is M-A-N-T-I-S-S-A. And then the other part here is the base. Okay, I shouldn't say that. It's some exponent of the base. Okay, I will just say that this is some exponent of some base. In this case, it is base 10 because the number is a base 10 scientific notation. So we are raising 10 to the power of 9 in this case. If you try to represent this constant in C and C++, it is usually written as 7.981 and then the lowercase e 9, because that is the way we represent a scientific notation in C, C++, and most programming languages that are derived from C or C++. So that's really just the syntax. Are we good so far? Is that still okay so far? All right. Okay. So there are also other types of representation. So if you look at a value, let me try to think of a different value here. What is the speed of light in meters per second? I think it's 2.9 million something, maybe. No, nobody, no physics, no one who has taken physics recently. Okay, let me go look it up. I know it doesn't matter too much in this class, but we'll just go ahead and take a look at it. Light speed. All right, so I was close. 299,792. Okay, so I'm going to write this down on the other side, and then we'll go take a look at this particular value, 299,792,458. Okay, there we go. And now I'm going to show you Zernal again. All right, so we have a pretty big number. It is 299 million. Okay, so it's close to 300 million something. So when you need to write this number out every single time like this, it's a lot of trouble, right? So now the question is, how do we use the scientific notation? Well, that's easy, because this number turns out to be the same as this number times 10 to the power of 0. Because anything to the power of 0 is 1. Any number to the power of 0 is itself. So that's correct. Okay, but that means it doesn't help us at all. So this is technically not a mantissa. We cannot really call that a mantissa, because a mantissa has to be normalized. And by means of normalized, I mean it has to be between 1 and up to, but excluding the base itself. So in this case, since we're dealing with base 10, the mantissa can only go from 1 to 9.9999999 and so on. We can adjust this portion, and also we can adjust the power of 10 until the mantissa, until we have a normalized mantissa. So the question is, how do I change this portion to be between 1 and 9.99999 and still preserve exactly the same value. What do I need to do to the exponent of 10 in order to preserve the same value? Let me pose the question like this, okay? So I want this equality to hold. I want one side to be 2.99792458. But what do I need to do about the power of 10, the exponent of 10, in order for the equality to hold? What do you think? So you just have to count, okay? You have to count how many times we have to shift the decimal point to the left-hand side, because there's an implicit decimal point right here, right to the right-hand side of the 8. So now we just have to count. 1, 2, 3, 4, 5, 6, 7, 8. So we have to shift it exactly 8 times. Every time we shift the decimal point to the left-hand side, we are making a value, we are basically dividing the value by 10. So in order to make up for the division by 10, we have to make up by multiplying by 10, but we can only adjust the power of 10. So that means the power of 10, or the exponent of 10, is now 8, like that. Are we still doing okay so far with how we quote-unquote normalize the part that specifies the, okay, if you look at this part here as the scale, this is the part that actually specifies the quantity based on that scale. So on one side we are saying we have 299,792,468 of ones. On the other side, we're saying we have 2.99792,458 of what? Of 10 to the power of 8. They mean exactly the same thing. However, this is what we need to have a mantissa. The mantissa can only be between 1 and up to, but excluding the base. Are we good so far about the normalization of what a mantissa means? Okay, all right. So now the next question is, how does this have anything to do with base 2? Well, I don't see any reason why this cannot be done in base 2. Okay, so I'll show you a few examples first, and then we'll go back to the discussion of a double precision floating point number. Because the first thing I want to show you is, let's try, let me see, 768. Okay, so 768 is in base 10, and now we want to look at this as a base 2 number. Okay, I'm waiting for the equal to come up. All right, so now we want to look at this as a base 2 number. 768 is 512 plus 256. So that means we have 1, 1, and then we have 8 zeros after that. So this is 1, 1, followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8 in base 2. All right, you look at this and go like, I don't see how this is in any type of scientific notation. Well, that's easy to fix, because I can always say times 2, because why 2? Because 2 is the base. We're now converting into a base 2 representation, so the base is no longer 10, it is now 2. Is that okay? All right, but remember, anything to the power of 0 is 1. So that means I can always say, doesn't do a single thing. I just do a little 0 as the exponent of 2. Are we good so far? But once again, we also have an implicit decimal point, in this case a binary point, to the right-hand side of the least significant digit, which in this case is right here. So if I want to quote-unquote get my mantissa right, okay, I just have to count how many times do I have to shift the binary point all the way to the left-hand side until I have 1 point, blah, 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 blah. Because in base 2, if I need a value that is between 1 and what we know as 2, we need the mantissa to be 1 point something. Okay? Is that still okay? Because in base 2, the value of 2 is 1, 0. So that's why we need the mantissa to be 1 point and then something. So now we just have to count. We have to count 1, 2, 3, 4, 5, 6, 7, 8, 9. We have to shift the point 9 times to the left. So that means if I were to rewrite this, I can now say, oh, this is just 1.1 in base 2 times 2 to the power of 9. Is that okay? What about all those zeros? Well, I mean, they're trailing zeros, so they don't really matter. I don't need to write them out. Is that okay? It's exactly the same method that I used earlier to convert a base 10 non-scientific notation, because we did not have a mantissa, to scientific notation where it has a proper mantissa. This time I just did it with a base 2 number. Okay? Is that all right? All right, okay. So let me get rid of the beeping first, because I have the notification reminder, because if I don't click to get rid of the beep, it will keep reminding me until I click it. But I don't see the notification. Oh, I'm going to turn off notification then. Do not disturb. Okay. There we go. Now it should not bother me. Okay. So now let's go back to what we saw earlier, which is in the browser. Okay. And specifically, we want to get back to the Wikipedia page into this picture. Now, if I want to conclude this class, with just one thing, I'm just going to look at these two representations, and I'm done. Okay, because if you look at, especially the second one is basically telling us what value is being represented by these 64 bits. Okay, let's take a closer look at what it is saying. I know certain parts of it may not be very clear. I will talk about and clarify those points. First of all, we start with -1 to the power of sign. The sign bit is one single bit. It can only be a 0 or 1. So -1 to the power of 1, in case the sign bit is 1, is what? What is -1 to the power of 1? -1, very good. So what if sign is a 0? What if the sign bit is a 0? What is -1 to the power of 0?
1.
Is 1. Oh, okay, so you can see how -1 to the power of sign is enough to basically say, oh, if the sign bit is a 1, we're dealing with a negative value, otherwise we're dealing with a non-negative value. Are we good? Okay, so that's done. Let's look at the second one, which is from 1 plus and then the sigma notation. The 1 plus, I think we got it, right? So whenever you see a sigma notation, and you go like, I have no idea what it is doing, you substitute concrete values into I. Then you can see where it starts. You can also see where it ends. Okay? So we're going to start with I equals to 1. What happens when I does equal to 1? Then we have B of 52 minus 1, which is B51. Where's B51? This is B51. It is the leftmost bit of the pink area, which we can also see as quote-unquote the most significant bit. But what are we multiplying that with? We're multiplying that with 2 to the power of -I. Remember what we made I? 1. So it will be 2 to the power of -1, which is 1/2, or 0.5, right? So that means this bit over here is telling us how many halves do we have. What do you think the next bit, or the one to the right-hand side, is going to tell us? We're dealing with binary numbers, so if 1 is telling us the number of halves, what do you think the one right next to it on the right-hand side is telling us? What the quantity of quarters, very good. And then eighths, and then 16ths, 32nds, 64ths, and so on. Are we doing okay so far? So if we go all the way to bit 0, which is this guy over here, that corresponds to when I equals to 52. Why? Because we substitute I equals to 52 into the rest of the sigma notation. So now we have B52 minus 52, which is B0. That means this particular bit here. But more importantly, what is it contributing to the sigma notation? It is contributing whether we have a 2 to the power of -52 or not. Now, is that a really small quantity? Yes, it is a very, very small quantity. So what we know is if you just add up this entire sigma thing, it can only add up to close to 1. If every single bit in the pink area is a 1, the sigma notation will only give us a value that is very close to 1 but not 1. It cannot reach 1, it's just getting there. Are we good so far? So when you add 1 on top of that, then you can potentially end up with a value that is close to 2 but not quite 2. But on the other side, if all the bits, all the pink ones are zeros, then you just end up with a 1. Oh, but that's exactly what we want as the mantissa, right? All right, that's good. So now we have the mantissa in base 2, which can only go between 1 and close to 2, but not exactly 2, times the scale, okay? The scale is 2 to the power of e minus 1023. So the question is, what exactly is e? Well, this is where Wikipedia did not quite explain, what e is. It just says the e is up there. The exponent field is an 11 unsigned integer, and that is e. Let me point out where we are talking about. So this is what we are talking about. The exponent field is an 11-bit unsigned integer from 0 to 2047. That is e. In other words, all we are doing is we are looking at the green area, looking at these 11 bits as if it is just an unsigned 11-bit integer. And we go like, okay, that is e, but e by itself is not telling us what we are raising 2 to the power of. By itself, it is not the exponent of 2 because we have an offset or a bias of 1023. Is that okay? So that means if the green stuff here is exactly 1023, we are talking about 2 to the power of 0. Okay? If the entire green area, if they're all zeros, then we are talking about negative 1023. Is that okay?
Why is it 1023?
Because IEEE says so. That's all I'm gonna say. Because IEEE said so.
Okay.
All right? I'm not kidding you. I'm actually telling you the truth. Because this is the IEEE standard. So at the time, instead of using the signed representation to look at E, they chose to use the unsigned representation and then have a bias of 1023 instead of 1024. But that's how they chose it to be. It's just chosen to be like that. The bottom line is we want the power of 2 to be able to go negative and also to go positive. So we want it to go negative to about 1,000-ish, and we also want it to be able to go positive about 1,000-ish. So IEEE chose to use they chose to use a bias so that the most negative exponent of 2 we can specify is negative 1023, and the most negative one, the most positive one that we can represent is 2047 minus 1023, which turns out to be 1024. Are we still doing okay so far with this expression here? So technically speaking, this is it. This is what a double representation is, and there's really not much to say about. If I give you a certain bit pattern, the 64-bit pattern, you should be able to figure out what it is representing. Okay? But I'm not going to leave you guys and just go like, okay, this is it, and in the next exam, in exam 2, not exam 1, in exam 2, I'm just going to give you a random bit, pattern, and then ask you what value it is representing. So I'm going to show you guys step by step of how to convert a value into the double precision floating point format, and also to do it the opposite way. If you're given a pattern, what value is it representing? All right? So that's what we're going to do for the rest of today's lecture. If we have enough time left, I can even go into the conversion part a little bit, which is basically what your next few labs are going to be about. The first lab today is about just math stuff. Okay, it's about base conversion. It is about finding the proper exponent. It's about getting an approximation to a specific value and so on. So it's not super specific to the double precision floating point numbers specification, but it's related because I need you guys to remember all the math that you have learned already at this point to handle the rest of what we need to deal with. All right, so let's go ahead and take a look at some specific value, and then we'll talk about how to do the conversion. So now we're going to take a look at certain specific examples. I'm just going to pick a number out of thin air. So let's just say it is 101 point, oh, I don't know. Let's try a 625. There we go. So this is the value that, oh, let's make it negative, okay, just to be a little bit more fun. So this is the base 10 representation of the value that I want to represent. So now the question is, how do we convert this into the double precision floating point format? Okay, so we're going to take it all the way to the 64-bit format, and then I'll show you guys how to double check and verify that I'm not lying to you, that I'm just pulling some zeros and one out of thin air and claim, oh, you know what, this is going to represent what we know of as negative 101.625. So that's where we are going at this point. So the first thing we want to do is to look at this and say, okay, how do we convert this into a into a base 2 representation? Well, the first thing is I'm just going to ignore the negative and just kind of focus on the absolute value. The reason why I want to do this is because I got a sign bit to deal with this. Okay, so just looking at this, I know the sign bit is going to be a 1 because the value being represented is negative. Is that part okay? In other words, if I go back to this pictorial representation, we are talking about, oh, you guys cannot see it. I don't know why. Okay, so let's try that one more time. There we go. So we are talking about this bit over here. The sign bit is going to be a 1 because we want the entire value to be negative, and the only way to make it the entire thing negative is to specify sign being 1, so that negative 1 to the power of 1 is negative 1. This is the only way we can make the quantity being represented negative. Okay, so with that done, let's move on and talk about, okay, what about the rest? What about just the quantity of 101.625? We want to convert it into base 2. So how do we convert a value into base 2? There are several ways, okay? If you're just starting to get used to the whole process, you might want to do something like this. So you can say, we are not going to have 128, right? Because the whole value is less than 128. So we're going to start with 64, and then 32, 16, 8, 4, 2, 1. And then we have halves, quarters, eighths, and so on. And at this point, I just need to figure out whether there is a 64 or not, whether we have a 32 or not, whether we have 16 or not, and so on. So that becomes more or less a comparison. We don't even need division here because you can only have up to 1 of 1 power of 2 to the power of something. So that means you just need a comparison. If it is greater than or equal to, we got 1. If it is less than, we got 0. So it's a very easy base conversion process because there is no division whatsoever. All right, so do you think there's a 64 in 101 something?
Yes.
Okay, we'll check that and say there's 1. What about 32? Once we have a 64 taken care of, we have what? 35 something, right? So do we have a remaining portion that has a 32?
Yes.
I think so, okay. So that would have taken care of 96. So 101 minus 96 is 5. So that means I probably don't have a 16 and do not have an 8. Does that make sense? Right? Okay. So we have no 16 and we have no 8. Now, if you are not if you cannot trust your mental math as much as, as much as I'm overconfident in my, mental math, you can always write it out on a piece of paper. Every time you say there is one of something, do a subtraction and deal with the remaining portion of what you need to convert. Okay, but I can kind of track it a little bit in my head. Okay, so I think we got 5 point something left, right? So 5 seems, there should be a 4 in 5, right? Check 1. But once you take care of the 4 in 5, you only got 1 left, which means we don't have any 2. But then we have 1, 1. Now we have just dealt with the 101. Now it's just the fraction portion. So what do we do with the fraction portion? Do not look at the fraction as 625 something. Look at it as, do we have a half in 0.625? Okay, yep, we do. And after we take care of the 0.5, we have 0.125 left. So with that portion, do we have a quarter? Nope.
No.
There's no quarter within 0.125. So there's none of the quarters and exactly 1 of the eighth, because 1/8 is 0.125. So now we have just converted the whole thing into base 2. And you can see the process is not super hard because there's no division involved. All you're doing is compare and subtract. That's all we have been doing. So the question now is, where do we put that decimal point? Now, decimal point at this point is going to be a misnomer because the whole thing is binary. So I'm going to call that a binary point, but nonetheless, it is still a marker so that we can separate the digit corresponding to 2 to the power of 0 from the digit representing the quantity of 2 to the power of -1. So where should I put it? I know it's hard for you guys to say.
Should it go in between the 2 and the 1 bit somehow?
You can specify the power of 2 between which 2 powers of 2?
The power of, the power of 1 and the power of 0. Between the power of 1 and the power of 0.
Okay, how about the value of the power of 2? Because we have 64, 32, 16, 8. So the point should be between which 2?
2 and 1.
Need close. Go ahead.
1 and 1/2.
1 and 1/2. That is correct. This is where we put the point because that is the whole point. No pun intended. The point of the point is it is a separator. It tells us where the negative powers of 2 start and where the non-negative powers of 2 start. Is that okay? I bet you in elementary school or whenever you learned your decimal point representation, your teacher never taught you, what is the point of the point. But that's basically what it is. All it is just a little marker and say, to the left-hand side of this, those are all the non-negative powers of whatever base you're dealing with, and on the other side are all the negative powers of the base that you're dealing with. That's basically what the point is. Okay, so now this is all in base 2. So you look at this whole thing, you say 1, 1, 0, 0, 1, 0, 1, point 101 in base 2. And this definitely does not look like scientific notation at all, right? It is just by itself a value. Where's my power of 2? Now, why power of 2 instead of power of 10? Because it is base 2. Everything is base 2 now, right? So now we say, oh, okay, fine. We'll give it a 2 to the power of 0. That never hurts anything because anything to the power of 0 is just 1. And in the multiplication, it is the identity. And as a result, it doesn't change the result of the multiplication. Okay. But I want something that's normalized. I want the left-hand side, I want this portion here to be a mantissa. So tell me again, what is the requirement of a mantissa in base 2?
To be between 0 and 10 or 1?
No, remember the base, okay? What base are we dealing with?
Oh, it's 2, right?
It's in base 2, so it has to be between
1 and 2?
1 and 2, excluding the 2, right? So 1 all the way up to really, really, really close to 2, but not quite 2 itself. Okay, very good. Okay, that's exactly what we need to do. So what we need to do is to shift the point or move the point to the left-hand side until the left-hand side of the multiplication becomes 1 point blah, 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 blah. Okay, so now we have to count. How many times do I have to move the point to the left so that we end up with 1.0, we end up with 1.10010 blah, blah, blah. 1, 2, 3, 4, 5, 6. So we have to move the point exactly 6 places. So that means this whole thing is going to be 1.100101 times 2 to the power of what? Every time we shift the point to the left, we have to add 1 to the power of the base.
6.
So we just have to now say, okay, it is 2 to the power of 6 right there. Are we good so far? All right. So I'm just going to emphasize that this is a base 2 number because otherwise, it is not absolutely clear. But I think I got it. Okay, let me just count again. 1, 2, 3, 4, 5, 6. Yep, 6 times. All right. So now you look at this, you go like, I still don't see how this become a 64-bit format that we know as the double precision floating point number, right? So what I'm going to do now is I'm going to just do some copy and paste just so that we can identify which portion is which portion and what we need to do with those individual bits. So let me just do one little thing here. I'm going to do the screenshot thing. I'm going to copy and paste this thing here. And we want to copy to the clipboard and then shift over back to here. And then from on my side, I'm just going to paste it here. There we go. It takes some time to show up. There we go. Yeah, not exactly the right size, but I think it will do. Okay. All right. The sign, we got that figured out, right? So we see this negative thing here. Okay, let me use a different color. Yeah, if anyone is colorblind, let me know if a particular color doesn't work out for you. Okay, because I'm not colorblind and I did not read up on color blindness, so I'm not aware of what color people cannot differentiate when they're colorblind. So this leads to the sign bit being a 1, which then is this guy here. So we know that sign is a 1. Okay, we got that. This part here is the mantissa. In other words, this entire thing is this entire thing in the parentheses. Is that okay? But someone is going to say, attack, that 1 here is not corresponding to any bit. It is not corresponding to any B of something. So what does that mean? That means the 1 point something, this 1 point something, the 1 to the left-hand side of the point is not explicitly represented at all. The reason why that is the case is in base 2, every mantissa has to start with 1 point. So once again, no pun intended, what is the point of representing the 1 to the left of the point when it is always there? Is that okay?
That sounds like a tongue twister.
Yes, that was intentional. The reason why we don't encounter situations like this in base 10 is because in base 10 the mantissa can range from 1 all the way up to 9.9999999 something. Okay? So that means the digit to the left-hand side of the point can be 1, can be 2, can be 3, all the way up to 9. We got choices. But in base 2, we do not have those choices because the mantissa in base 2 can only range from 1.00000 all the way up to 1.111111. So that means every single mantissa is going to start with 1 point. So why do you want to waste 1 bit to represent something that is constant? The answer is nope, we're not going to do that. Okay, so that means only the fractional part of the mantissa. Let me use a different color. I'm gonna use orange this time. So only this part here matters. Only that part needs to be represented. Is that okay? But when you look at the orange portion, what is it saying? It's telling us how many halves, how many quarters, how many eighths, how many sixteenths, and so on, right? Look at these guys, 2 to the power of negative I. But what is the range of I? I goes from 1 to 52. So that means we are actually specifying the presence or the absence of halves, quarters, eighths, sixteenths, and so on. So that means the orange portion is corresponding to the sigma notation. Okay, so I'm gonna make a connection between those two, like so. Is that okay? So I think we got most of it taken care of, except for the 2 to the power of 6, right? So now we look at the 2 to the power of 6, and we go like, let me use yet another color, which is bright green. We look at this 6 here, and we say, I think this portion here is trying to specify that 6, because that's the only thing left, right? Is the scale. What is the unit here? The unit is 2 to the power of 6. So now what do we get? Okay, okay, let me just write this out so that we have E minus 1023, which is in base 10, has to equal to 6, which is also in base 10. Can somebody solve E for me? If it takes you more than 5 seconds, it's too long. Yes, go ahead. It will be 1029. Very good. So this solves for us, and E equals to 1029. This is algebra. All right? You look at this and go like, attack, aren't we supposed to do everything in base 2? Sure, we'll do it in base 2. So now we're going to convert 1029 into base 2. So what is it going to look like? Well, I can recognize 1024. Once we take care of the 1024, we have a 5 left, which is a 4 and then a 1. Are we good so far? Can you see how I broke a particular value down to a summation of powers of 2? All right? So if you're not familiar with all the smaller powers of 2, I can remember all the way up to maybe 2 to the power 15 or so. Okay, once we get past that point, it gets too many digits. Okay, but for the first, I would say 10 to 14, powers of 2. In time, I think all of you would have those memorized. It helps to have those memorized, not for a class, okay, not because in certain exams you'll be able to do it faster, just because as a job, as a software engineer, as a developer, you are going to kind of need that, need those memorized and be able to quick to do all this math in your head. Now, do we have calculators that can do this? Absolutely. But at some point, it's just mentally helpful to be able to do it by hand as well. Okay, so I'm just going to claim this is 1 followed by 10 zeros, because 1024 is 2 to the power of 10. This is another trick that some of you may find helpful, is to approximate. Every time you see 10 to the power of 3, it is about 2 to the power of 10. This is how I can tell how many bits is needed in order to represent the number of people on Earth, which is about 8 billion, right? So in terms of thousands, what is 1 billion? It's 1,000 to the power of what is 1 billion? Three, okay? It is 3.
Isn't that a million though? 1,000 to the power of 3 is a million?
1,000 to the power of 2 is 1 million. And then 1,000 to the power of 3 is a billion. Okay, so, all right. But since I said 1,000 is about 2 to the power of 10, so how many binary digits do I need to represent up to 1 billion? So it's 2 to the power of 10, the whole thing to the power of 3. So it's 3 times 10, which is 30 bits. Okay, we need exactly about 30 bits to represent a quantity up to 1 billion. But then we also have the 8, right? We have close to 8 billion people now.
These
So-
multiply by 8.
So now we need to take the log 2 of 8, which is 3, because 2 to the power of 3 is 8. So altogether, we need about 33 bits. Okay, we need 33 bits to count the number of people on Earth. I can do all that without a calculator, without using log, because I remember that, just quick rule, okay? 10 to the power of 3 is about 2 to the power of 10. So for approximation purposes, it works out in most cases, unless you have that one boundary case or a few of those boundary cases where one estimate is going to be too big. All right. Okay. So enough of that. So now we say this is 1 followed by 10 zeros, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Except now we have to change 2 of those zeros into ones. This is the 1, so turn that into a 1. And then this is the 4, turn that into a 1, 2. Now we have E. Are we good so far? So now I think we got all the bits that we need, because now the only thing left to do is to stitch, quote unquote, stitch all the bits together. Kind of imagine that we have the head of Frankenstein, we have the torso of Frankenstein, and then we got the limbs of Frankenstein, which is over here. So now we just have to stitch, Frankenstein back together from the parts, from the components. So how do we do that? Well, I'm going to copy and paste from the Wikipedia page again. It's nice to be using Wikipedia because I'm not infringing on any copyright, if I do that. All right, so once again, I'm going to take a screenshot here. And I'm going to have to do that using my mouse. Here we go, and let's switch back to Zernal. I'm gonna do a paste, maybe here. That looks good. Okay. All right, so now we need to stitch everything back into one thing. So I'm gonna use the color coding thing again, although I wasn't absolutely consistent. The sign bit here is going to the sign bit over here. The exponent, which I now use the proper color scheme. This is my exponent. That goes to the green portion here. What is left is what we call the fractional part of the mantissa. So that's in red, or I think fuchsia, magenta is closer. So now we look at the magenta portion, which is this portion here. And then we say, that's going to go here, starting from the left-hand side. Is that okay? Well, let me do a slightly better job. This end here goes all the way to this end over here. So now we have the most significant bit going to the most significant bit. This is how we stitch the whole thing back together. The rest are all zeros, because I did not specify the other zeros. I'm sorry, I do have to apologize to the people in the back, because it's harder for those people to see the bottom. Let me see if I can, it's hard to scale this now. Can you guys in the back still see this? Okay. You can stand up if you want to, just to take a glimpse of this portion. I did not think about, not using the last portion of the screen, lowest portion. So are we doing okay so far? So we got a 1 at the green portion, which is the sign bit, and then the 11 green bits correspond to the biased exponent, which is 1 followed by 7 zeros, and then 1, 0, 1. And then the pink portion is corresponding to the fractional part of the mantissa in base 2, which is 1, 0, 0, 1. 0, 1, 1, 0, 1, and then the rest are all zeros. We just pad zeros all the way to the right-hand side. Are we good so far? Yes? No? Maybe? Questions? Right? So if there are no questions, now one exercise that you guys can do is to reverse the whole process. Okay? Given the bit pattern, which I'll give you in just a little bit, reverse the whole process. Use the math expression to get back to the value that it is supposed to be represented. You should get back to negative 101.625 in base 10. So that will be an exercise for you guys to do. But for now, I'm just going to claim that that is the case. So what am I going to do now is I am going to give you the exact bit pattern. We have 1, 1 as the sign bit. And then for the exponent, which is biased, is 1 followed by 7 zeros. Let me just do the counting here. Yep, 7 zeros. 1, 2, 3, 4, 5, 6, 7. And then 1, 0, 1. That is the green portion. And then the pink portion, which is the fractional part of the mantissa, is just, not 2. It's going to be a 1, sorry. So, and then we have the fractional part of the mantissa, which is what appears to be pink in here, but it is using the magenta line. So that is 1, 0, 0, 1, 0, 1, 1, 0, 1, and then the rest are all zeros. This is the 64-bit representation using the double precision floating point way of interpreting the 64 bits. This is how we represent the value of negative 101.625 in base 10. All of you are going to go like, well, Tech, you could have just pulled a bunch of random zeros and ones and claimed that is representing negative 101.625, and we wouldn't know any better. Well, you should, because you should be able to follow each and every single step and double check that I did not do my math wrong. However, what I'm going to do now is to say, well, do we have a way to verify it? Do we have a way so that in case my own math is messed up, I will still be able to double check what value is being represented by this particular bit pattern? But before I go there, are there any questions? Are there any questions about the 64 bits of a double precision floating point number is not to be considered as one single value, but to be interpreted as 3 different parts. The 3 different parts play different roles in terms of what it is doing when we try to come up with the values being represented, which is summarized by this expression here.
I have a question about bit 63, the sign one. So that one says always 1? Or
Which one? Sorry.
63? The sign
63.
The sign.
No, it's a 1 because the value that we were trying to represent was negative 101.
So it's probably be the same number but just 0 in the front. Or just
It would have a 0 here instead of a 1. The rest would be the same, yes.
Okay.
Very good.
Then do you want to even show a trailing 0?
Hmm?
Or do you show trailing 0? Like the 0's first, are we going to show it? Or
Yes,
Okay.
so this is the 1 because we have a negative value.
yeah.
But if we had a positive value, it would have been a 0 here.
Okay.
All right, so the first thing we need to do is to look at these 64 bits and go like, but there's no way to enter a really long, there's no way, not even long, there's no way to enter a bit, a number in base 2 in C or C++. Well, that's kind of a bummer because now we cannot just kind of type this number in and do something to verify that this is right. So we'll do something better. Okay, we'll convert this to base 16. Okay, so now we are kind of doing a segue to base 16. So let me start a new page after, and now our focus is now base 16. So in base 10, we have digits from 0 to 9, right? So what about in base 16? We have digits going from 0 to 15. What we know as 15, okay? I should emphasize what we know as 15, which is a quantity, it is a value, but how it is written is a little bit different, okay? So we'll go for the ones that we know really, we are quite sure about, okay? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now we need to represent 10. But I'm not going to write down 1, 0, because this is in base 16, so the quantity of 10 is supposed to be representable using a single digit. And then you go like, but we don't have a single digit to represent 10. You'll be right. So what we need to do now is to borrow from letters in the English alphabet, okay? Now, why, the English alphabet but not the German alphabet or the Latin alphabet? Well, it really has to do with, computer science was most developed in English-speaking countries initially. So that's why, they chose to borrow from the English alphabet, which is also because ASCII only has U.S. English alphabet. What does ASCII represent? ASCII? I mean, you guys probably have heard of ASCII code, right? What is the ASCII code of, whatever punctuation or whatever letter or whatever digit? What is ASCII? What does it stand for? ASCII?
Maybe it starts with American.
American Standard Code for Information Interchange. That's
American.
ASCII, okay? It's American. But then you go like, well, but there's North America and South America, and North America has 2 countries, and then South America has many other countries using different alphabets. Well, I think they're referring to the United States of America. And that part was never really spelled out, but I think it was implied. So A represents 10, B represents 11, this is 12, 13, 14, and 15. Now we have exactly 16 digits, each one representing a specific value, ranging from 0 to what we know as 15. So the next question is, what about the conversion from base 16 to base 2? Do we need to do a bunch of division by 16 and mod 16 and stuff like that? The answer is, well, if you start with base 2, you don't have to do much, because each base 16 or hexadecimal digit represents exactly 4 binary digits, which is great, okay? Because a base 10 digit is representing 3 and something of a bit of binary digits, which is problematic because there's no way we can just go like, oh, okay, this digit in base 10 are these 3 digits in base 2, and so on. We cannot do that because it's not even a rational number. But in base 16 and base 2, it is. And why do you say that is the case? What is the special relationship between base 16 and base 2 that is absent between base 10 and base 2? I think you got the right idea. 16 is 2 to the power of 4. But somebody is going to say, but 10 can be expressed as 2 to the power of 3 point blah, 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 blah. So what is the big deal here? The big deal is the blah, 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 okay? Because the rational number, which serves as the exponent of 2 to get to 10, is an irrational number, okay? Which means the digits just keep on going and going, and it's not even recurring. But in base 16 versus base 2, it is just 4, as in 4.0, 0, 0, 0, 0, 0, all zeros after the decimal point. That is why it works out so nicely. So now we look at 0. I don't think anyone's going to argue that 0 is 0, 0, 0, 0 in base 2, right? So I'm going to be clear that this is in base 16, this part is in base 2. That's just the base. Okay, let me just emphasize that we're looking at the base here. So this is 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. You don't have to copy this because you can find this online. But I'm just writing it out so that you guys can just visually see the dynamic of how I feel out of the table. It should be boring by now, because I'm just adding one. This is a great opportunity to see if you remember how to do base 2 addition, because all I'm doing is just adding one to each row and go like, okay, this is the next one, and so on. There we go. So now we have a nice table. Every time you want to go from base 16 to base 2, you just go, look up the base 16 digit, pick up the 4 bits, slap it in. What if you want to do the reverse? You start with base 2 and you want to convert to base 16, to the opposite way. Grab 4 bits at a time, look up the base 2 column, and then find out which digit in base 16 it is the 4 digits in base 2 are corresponding to. That's it. It's table lookup. Did I mention no division and no mod, no remainder, no multiplication, nothing like that? It's really just looking up a table. All right. Okay, so now, what does that have anything to do with what we have been talking about? See this bit pattern here? It is wrong. If I were to write this entirely out using base 2, all binary digits, it's going to be 64 digits, which is long. I don't want to deal with that. And you cannot do it in C anyway. You cannot specify a base 2 number in C or C++, but you can do that in base 16. So we are going to do a copy and paste. Okay, so paste. There we go. All right, so now we can pull this back up again. So now we look at this binary bit pattern and go like, okay, how do we represent this in base 16? Remember what I said? Divided by chunks of 4. Now, technically, you're supposed to do the division from the right-hand side, from the least significant bit. But since we know there are 64 bits exactly, so that means in this case, I can safely do it from the left-hand side as well, because there is a whole number of 4 in 64. In other words, 64 divided by 4 is exactly 16. So I don't have a problem of, maybe something is going to be misaligned. Nope, they're going to align just fine. So what we do is we look at the chunks of 4. So chunks of 4, chunk of 4, chunk of 4, chunk of 4, and then chunk of 4, like that. And then the rest are all zeros. Is that okay so far? Does everybody see how I broke up the zeros and ones into groups of 4 bits? What do we do after that? I mentioned that earlier. Just look up. It's just a table lookup at this point. So I don't even need to look up the table because I've done this so many times, not because of my teaching job, but because of all the code development and stuff like that. So I can just look at this and go like, this is a C, that's a 0, that's a 5, that's a 9, that is a 6, that's an 8, and then just a bunch of zeros after that. All right, well, you cannot just say a bunch of zeros when you're specifying constant in C or C++, right? We kind of have to figure out exactly how many zeros there are. So let's double check. Okay, so we have C0, 5, 9, 6, 8, and then the rest are all zeros. So now we just count how many digits we have counted so far. I've just done some counting here. 1, 2, 3, 4, 5, 6. So out of 64 bits, we have taken care of how many bits? Remember, 1 hexadecimal digit corresponds to exactly 4 bits. Now that we have 6 hexadecimal digits, how many bits have we specified already? 24, very good. So how much is left? 64 minus 24 is 40. And since each hexadecimal digit is corresponding to 4 bits, so how many zeros do I need to pad on the right-hand side? 10 zeros, very good. All right. So I think we're getting the hang of this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In C and C++, if you want to specify a hexadecimal digit, by the way, what is hexadecimal? Why is it called hexadecimal? I know most of you have heard of hex, right? What is the hex representation? But it's actually hexadecimal. What is hexa? Hexa is That's penta.
Six.
Hexa is 6. Okay? So when you say what is the hex code of something, you're talking about base 6. That's a really odd base to use. It's just as bad as base 10. So so we are not talking about hex. We are talking about hexadecimal. Hexa is the 6. Deci is
The 10.
the 10. So when you add up the 2, what do you get? Base 16. Exactly. Okay? So now, the 0x is the prefix. So if you want to specify a constant using base 16, you say 0x and then a bunch of hexadecimal digits. That's how you do it in C and C++. All right. So somebody's going to say, but Tack, you still have not answered your original question. You're just converting the bunch of zeros and ones into a bunch of hexadecimal digits. We still do not know whether it is representing negative 101.625 in base 10. Well, we're getting there. I mean, we're getting there. All right, so next I'm going to write a program. I don't think I kept the program from my Thursday class, so I'm going to rewrite it. Well, even if I had it, I'm going to rewrite it anyway. So let me see if I still have it. Yep, nope, that's different. So never mind. So we're going to rewrite the program to begin with. I'll just call it test.c. So there are a few techniques here that can be useful, maybe not instantly, but over time it will be useful. The first thing is the library that I call standard integer. That's why it's called stdint. Std is standard, and then int is integer. This gives us a lot of definitions, including type defs. And here's the main. And it's going to return the 0 at the end. And then now I specify a 64-bit unsigned integer that I would just call x here. And I'm going to say x equals to that value that we were looking at earlier. All right, so let me see what is the best way for me to see both at the same time. I think that will work. So we have 0x C05968, and then 10 zeros. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There we go. And that's my entire program. So it is important to learn how to use uint64_t, because what that is specifying is an integer that is unsigned, but it has a width of exactly 64 bits. This code will compile, and x will still remain as a 64-bit unsigned integer. Doesn't matter what architecture you're compiling it to. So if you say, what if this? If I compile this program in Arduino, which is a 16-bit platform, would that x still be 64-bit wide? Yes. If I use a really old PC in 32-bit mode, would that x still be 64-bit wide? Yes. Okay. So once you know what range or how many bits are needed to represent the values that you're going to put into a variable, this locks down the width of the variable. It makes sure that nothing is up to the compiler to decide. Because otherwise, the compiler can go like, well, the native platform here likes 16-bit integer. I'm just going to use 16-bit unsigned integer. Nope. This spells out it has to be exactly 64-bit wide, which is really useful, which is important in this case. All right, and I'm going to claim this is the entire program that I need to verify that the number that we have been dealing with is correct. Okay, so we'll take a look at how we can use this rather simple program to do it. I mean, this program doesn't even have cout or printf or anything like that. How do we check? How do we do anything with this program? I mean, if you run this program, this is what happens. It's like, what is going on here? So this is also one thing that is really important that I wish other professors would have taught you up to this point, which is the use of a debugger. Okay, it's really, really important to know how to use a debugger. I'm only using a debugger just for instructional use at this point, but if you really have a program to debug, it is extremely useful. So B7 is put a breakpoint on line 7, which is right before we return from main. Okay. And R is run, so I'm now running the program, and I have now hit what we call a breakpoint, which means the program has not stopped, it has paused. The difference between stopping and pausing is if you have paused something, you can resume. But if you have stopped something, you cannot resume. You guys are way too young to remember what is a VCR or cassette tape player, because usually there's a pause button versus a stop button. If you click the pause button, you can resume playing the tape. It will, really quickly. If you hit the stop button, all kinds of mechanical sound would happen, because it would actually take the head, the video playing head away from the tape, so the tape is actually completely disengaged if you click the stop button. But anyway, getting back to the debugger. Okay, so if I were to print X, it would be the value that we put into it. And it's going to be like this. It's like, what? That's not what we put into it. This is the base 10 representation of that base 16 thing, right? So if you want to say, I want to look at the base 16 version, sure. I mean, just do a /X for hexadecimal representation. Okay, now we're feeling better. But still, we're not getting back to negative 101.625, right? I mean, all we are playing with here is, this is the base 10 representation of the unsigned integer. This is the hexadecimal representation. If you want to, you can even use base 2. If you really worry about, do we have the right zeros and ones? Yeah, I think we got it, okay? But none of this is negative 101.625. How do we get that back? So one thing that people may say is, well, I think we can do a cast, right? This is typecasting. I hope you guys still remember what is typecasting. You should have learned typecasting in CISP310. Okay? No? Oh my goodness. Okay, casting is coercing a value into a specific type. So in this case, I'm taking the value of X and try to coerce it into a double, as a type. And you press the enter key and go like, oh man, that's not working, Tech. What is happening here? The reason why this doesn't work is because before the casting, it is looking at the value of X, which is exactly what we saw earlier, okay? Which is that number. So it is basically coercing to say, we want to represent this value as a double. That's basically what the typecasting operator is doing here. Is that okay? And that's why it didn't work. So what we need to do is a different trick. So let me see what you guys, how much you remember from CISP360. What is that?
Reference.
The address of, right? Okay, so ampersand as a unary operator is address of. So if you did not encounter address of, your professor never taught you address of in CISP360, you have some topics to catch up with. I have to say that. Okay. Okay. This is the address of. Okay. Very good. So if I were to press the enter key, it goes like, okay, the address of. This is the location in memory, but this is the type of that value. Okay. We are looking at the address of a uint64_t. Yeah, sounds reasonable, right? Because X is, after all, a uint64_t, so this is the address of that. Okay. So now we'd say, let's do that. What is that doing? Well, once again, it is a typecast operator, but what am I casting in this case? I'm not casting X. I'm casting the address of X, which used to be a pointer or an address to a uint64_t. In other words, to spell out longer, ampersand X used to be the address of a 64-bit unsigned integer. I go like, wait, hold on a second here. I don't want to look at it as an address of a 64-bit unsigned integer. I want to look at that as the address of a double. I'm not changing what is at that location. It's still the same 64 bits. I'm just telling the debugger to say, well, it's no longer the address of a unsigned 64-bit integer. Now it is an address of a double. But if I press the enter key, nothing magical is going to happen because it is still at the same address. Is that okay? I'm just rezoning, okay? Instead of, this is now, it's no longer a single family house, it is now a commercial property. But it's still the same structure, it's still the same address, it's still at the same location, right? But what you can do with it is different. Okay? So with a commercial, building, now we can park like, 20 vans, up and down the driveway, and nobody's gonna complain about it because it is now commercial, okay? So likewise, if I say this, now what is that? What is the asterisk doing here?
Isn't it saying what's inside,
Close.
like what lives at that address, the value?
Exactly. It is called dereferencing. Okay, it is dereferencing an address or pointer. So it is basically saying, tell me what is the value at that address. But what am I dereferencing? Am I dereferencing the address of an unsigned 64-bit integer, or am I dereferencing a double? I'm dereferencing a double, because if I were to put extra parentheses just to emphasize the order of operation, now these parentheses are not really needed. I'm just putting those things in just so that it is clear about the order of operation. So by the time I get to the dereferencing, it is already saying, oh, you're giving me the address of a double. So I'm going to interpret what is at that location as if it is a double. Did I put something into there, as a double? No, I did not. Okay, I said, well, I'm looking at this as an unsigned 64-bit integer, and I'm just sticking in a bit pattern over there. But at this point, it is going to interpret those zeros and ones as if those are the bits of a double. Is that okay? So let's see what's going to happen here. It's magical, isn't it? No, it is not magical. This is all based on operators in C that you have learned, that you should have learned in CISP310. And I feel really, really, really sorry for people who took Java, because Java has no dereferencing, has no address of, and it does have typecasting, but there's no pointers to cast, there's no address to cast. So people who took a Java class instead of a C++ class to get into this class would also have some catching up to do. Are we good so far? So this entire exercise, okay, is basically just to look at the value of what we see as negative 101.625 and convert it into the 64 bits of a double precision floating point number, and then get back to verify that it is indeed representing negative 101.625. All right, so I'm going to do one last thing, and I will ask you guys here what would be the value, okay? And that will be the entire lecture, and then we switch to the lab. And I did set up the time of the lab incorrectly, but I'll fix that later. So if I were to change this 101 here to, let's say, 110, what do you think what am I doing to the value? Let me say that one more time, and this time I'm going to use a mouse pointer so that this way the video records that too. Yep, it's still recording. So if I were to change this 01 into 10, okay, what do you think would have changed in terms of the interpretation as a double? So the first thing you have to do is to say, okay, which portion of, because we got three distinct portions, three distinct fields within the 64 bits. So the first thing you need to know is, okay, which field am I changing, right? So we count. This is bit 63, 62, 61, 60, 59, 58, and okay, I'm gonna skip. This is bit 52, and that is bit 53. So I'm just changing, I'm doing a microsurgery on only bit 52 and bit 53. So which portion do they belong to?
Is it the exponent?
The exponent, very good, okay. So I'm basically bumping up the value of the exponent by what? I'm changing a 01 into a 10, and those two turn out to be the least significant bits of the exponent. So what am I actually doing to the exponent value?
Increasing it by 1.
Increasing it by 1. Very good. Okay, so if I increase the exponent of 2 by 1, this has nothing to do with the bias, by the way, because the bias remains the same, right? So it doesn't even matter what the bias is. So what am I doing when I increase the exponent of 2 by 1? What am I doing to the value being represented? So instead of blah, blah, blah times 2 to the power of 6, it is now blah, blah, blah times 2 to the power of 7. What is that doing to the value? Doubling. Very good. Okay, we are basically doubling the value by 2. So let's play with this, right? Set var x equals 2, 0x c 0. So instead of a 5, we have a 6 now. And then the rest would still be the same, which is a 9, 6, 8, and then followed by 10 zeros. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so setVar is a GDB command to change the value of a variable. Yes, so you can actually do that in a debugger. Once you pause the execution of a program, I should say this, once you pause the execution of a program, you can change the value of variable memory locations and whatnot before you continue the execution of the program, which I'm not going to do, but I am going to reinterpret what is at that location. So now it should say negative 203.5, I think. Because if you double 0.625, it is 1.5. Oh, okay, I was wrong. It's negative 203.25, which is double the value of negative 101.625. Okay, so I was able to kind of do some micro adjustment to the bit pattern and see how it is affecting the value being represented. Okay, so this is the sort of little exercises that you can do. Once you get to this point, you can play with it and see, oh, okay, so you can also go the opposite way. Okay, I'm going to show you this and then I'll truly be done. Okay, so what you can do is to do the opposite, which means you are using the casting trick that we did earlier, but this time you're doing it on the other side. So you can now say, I'm going to store a double into that location, even though the location really belongs to an unsigned 64-bit, but you can also do it exactly the other way, which is something like that. And now you can look at the bit pattern and double check to see if the bit pattern makes sense. This part is all getting recorded, so you can actually do this exercise on your own, assuming you have access to GDB or something that is based on GDB. VS Code can use GDB and GCC. Okay, so if you have VS Code already installed, you can look up online and find out how to use GDB along. I mean, most debugger can do something like that. It's just a matter of what is the syntax or what button to click or what icon to click to get this done. All right, so this is concluding today's lecture, and let me give you the lab for today. And let's see, where is it? And I forgot to take row. That's okay. It's not super important. All right, so I set up the time wrong. Oh, yeah, that won't work. That won't work with it. I'll give it 1:25 p.m. 1:25 p.m. I think that should do it. Oh, the access code is double, not surprisingly. So if this is double, don't you think there has to be a single somewhere? The answer is there is a single precision floating point number format, which is only, guess how many bits it's going to take?
8.
No. The double takes 64,
Oh, 32.
so the single is going to take 32. That's right. Yeah, but these days, no one is using single precision floating point number anymore. So, all right. So you should be able to get into the lab now. I can just use participation of the lab as role. Kind of makes sense, right? I mean, yep.
On our hexadecimal, the only thing I missed is where the 0x came from. You guys mentioned about
Oh, 0x is a prefix.
Just on any accidents.
Yeah, so this is how C compiler can tell, how should I interpret the rest? Is that a base 10 number, is it a base 8 number? Because you can use base 8 too, or is it a base 16 number? So 0x is telling the C compiler what follows are hexadecimal digits.
Okay, sweet, thank you.
All right, so this is one of those labs as usual that you can try many times, and it only maintains the highest score. So if you don't get it the first time, you can try again. I will stop the recorder and get the video uploaded.